All right, well, welcome to our recording for the final exam review session. I'm going to start by going over the document that was labeled Part 2 because this is the one that emphasizes the new material. And then later I'll have a look at Part 1, which reviews the older material. All right, let's go ahead and have a look at our final exam review sheet, Part 2. Okay. First problem here, it gives us really first 5 problems, same directions. It says find all numbers for which a rational expression is undefined. If it is defined for all real numbers, state so. Okay. Okay, now a rational expression is generally defined for all values of x except any values which might make the denominator equal to 0. So generally our approach is going to be to take the denominator and set it equal to 0 and then solve whatever little equation that generates. Okay, so if I set 5x equal or minus 45 equal to 0, I can add 45 to both sides and get 5x equals 45, and therefore x equals 9. So this particular rational expression is defined for all values except x equals 9. And since they asked us to find the values where it wasn't defined, let's check the wording again. Find all numbers for which it is undefined. Okay, well that's our answer. X equals 9. Okay. For the second rational expression, same approach. We're just going to take the denominator, set it equal to 0. In this case, I would divide both sides by 2 and get that x equals 0 is the only number for which this rational expression is undefined. Alright, third example. So again, I'll take my denominator, set it equal to 0. Okay. Now, if I try to factor this, this is a sum of squares, so there's no particular formula for that. Okay, I could try to solve for x and get x squared equals negative 9. Okay, but then that means that we're looking for a number whose square is a negative number. Okay, no real number satisfies that. Okay, there's no real number that when you square it you get a negative. Even negatives, when you square them, become positive. So no real number satisfies this. Okay, so what did the problem say again? The instructions said, if it is defined for all real numbers, state so. Alright, well, this problem would be exactly what it was referring to. Okay, so in this case, the correct way to write our answer would be defined for all real numbers. Let's see if I can write that just a little better. All real numbers. Alright, number 4. Alright, so in this case, the denominator has 2 factors. Doesn't really change my strategy though. Okay, I'm going to set the denominator equal to 0 to see if there's any x values that make the denominator equal 0. Okay, well, since my denominator is a product of 2 factors, I can say that if either factor equals 0, since 0 times anything is 0, that makes the entire denominator equal to 0. So I can split this into a compound equation, x plus 3 equals 0, or 4x minus 7 equals 0. So x equals negative 3, or, well, let me see, 4x equals 7, which would be the same as saying x equals 7/4. So in this case, there's 2 solutions. Okay, one nice way to write your answer when there's 2 solutions is just to write a little discrete set. The symbol for a discrete set is what we call a brace, or some people just call it a squiggly bracket if they can't remember the word brace. Okay, that's how I would write my answer for number 4. Okay, it's a set of two values for which the denominator is undefined, -3 and 7/4. Alright, there was one more of this type, problem 5. Okay, same strategy as before. We're going to take our denominator, set it equal to 0. Now, my denominator is quadratic, which suggests factoring it and trying to make it similar to the last problem. So, we'll see if we can factor this trinomial into two binomials. Since the trinomial leads off with an x squared, the binomials would each need to begin with an x. And now I'm looking for two numbers that multiply to -6 but add to -1. Okay, -3 and +2 come to mind. So now I'm going to translate this to a compound equation. Okay, x minus 3 equals 0, or x plus 2 equals 0. So that gives me two solutions, x equals 3 or x equals -2. Okay, so those are the two numbers for which my original rational expression was undefined. Okay, so again I'll write my solution set using the notation for a discrete set. Okay, it's convention to go from least to greatest, so I'll write it as -2, 3. And that'll do for number 5. Now let's have a look at our review sheet again. Okay, problems 6 through 12. Simplify the rational expression. If it cannot be simplified, state so. Alright, well let's do these problems then. Alright, in problem 6, we're given x plus 2 over 5x plus 10. Now to simplify a rational expression, we're going to make use of the fact that division and multiplication are inverse operations. Okay. What that means is that since there's already division built into a fraction naturally, we're going to try to rewrite either the top or the bottom or both as factors in factored form, so that there's multiplication that can be canceled against the division. Now in the top, x plus 2 is prime. It can't really be factored any further, so I'll just treat it as a single factor. In the bottom, there's a common factor of 5 that I can factor out, and that leaves a factor of x plus 2. Okay, now I can make use of the fact that division and multiplication are inverse operations. I can cancel out those x plus 2's, and that leaves me with just 1/5. And 1/5 is the simplified form of our fraction in number 6. Okay, we'll do something similar in number 7. Now again, the numerator doesn't really factor. Okay, so I'll write that as x minus 3. Okay, in the denominator, I have a difference of squares, 3 squared minus x squared. So I can factor that as 3 minus x times 3 plus x. Now, as everything's written, there's not really anything to cancel. But there is one little trick I can do to make it so I can cancel. Okay, anytime I have a difference, if I factor a -1 out of the difference, it reverses the order. So there is one thing I can do in the numerator. I can rewrite that as -1 times 3 minus x. And when I do that, that will enable me to cancel with a factor in the denominator. So I get -1 over. Now this 3 plus x, you could write it as 3 plus x, or you could write it as x plus 3. With addition, the order doesn't matter, so you can change it at will. With subtraction, you can only change the order by factoring out a -1. Alright, there's our answer for number 7. Let's keep moving then. Here's number 8. Okay, x plus 3 over x squared plus 9. Alright, so again, the top cannot be factored. Let's look at the bottom. The bottom is a sum of squares. There's no specific factoring formula for a sum of squares. Now sometimes you could do something else, like factoring out a common factor in a sum of squares. But in this case, there is no common factor. Okay? Because I cannot factor then either the denominator or the numerator, there's really no way I can cancel. I can't do any canceling the way it's written because I'd be canceling addition against division. I really have to factor it before I can do any canceling. So this one cannot be simplified. It is simplified. It might actually be a little better to say cannot be simplified further because it is simplified. But I would know what you meant either way. Alright, now in number 9 it does look like there's some opportunities to do some factoring. I see in the numerator there's a common factor of x, and if I factor that out I get x times x minus 3. Now the denominator is already really factored. X minus 3 squared. That square just implies that there's already two factors of x minus 3 here. I can cancel one of them, and that leaves me with x over x minus 3. And that's as much as I can do for number 9. So there's the simplified form of this fraction. Alright, looking then at 10. Well, it looks like I can do some similar things here. Looks like I can factor out a y in the numerator, and that will leave me x minus 2. Now in the denominator, I can clearly take out an x, and that would leave me 2 minus x. So again, I reach this point where these two factors are the same except opposite order. Okay, since they're both subtraction factors, in order to change the order of either one of them, I'd have to factor out a negative 1. Now I only have to change the order of 1. And I can really change the order of either one to make the cancellation happen. But it's kind of a convention that if there's going to be a floating factor of negative 1, we leave that on the top. I personally don't actually think that's a really critical rule, but it is something that you'll see done fairly consistently. So to stay consistent with practice, I will do the same. So I will choose to factor negative 1 out of the top. That'll give me a negative y times 2 minus x over x times 2 minus x. And then I can cancel those factors of 2 minus x. And my final answer for number 10 will be negative y over x. It would also be fine if you put the negative out in front of the fraction. Alright, number 11. Well, here my numerator and denominator are both trinomials, so I will attempt to break them into binomials. So let me see. M squared plus 2m minus 3. The first term is m squared, so that tells me that the binomials for my numerator should both start with an m. And then I need two numbers that multiply to negative 3, but add to positive 2. Not a lot of choices for multiplication to negative 3. We're either talking about negative 1 and positive 3, or positive 1 and negative 3. I'm going to go with negative 1 and positive 3 because those add to positive 2. Now, come down to the denominator. The first term is 2m squared. So that tells me that over here, when I break that into binomials, one of my binomials needs to start with a 2m, and the other just needs to start with an m. Now, I need two numbers that multiply to negative 1. That's pretty much going to have to be 1 and negative 1. But I'm going to intentionally put the negative 1 on the outside, and I'll tell you why. I want the negative 1 to pair with the 2, so that when I multiply the outer terms I get negative 2m, and when I multiply the inner terms, I get m. Okay, which negative 2m plus m is negative m. Okay, and that's what I'm going for. I'm trying to get the inner to work out. Alright, well, now that I have factored the numerator and the denominator, I see that I can cancel some factors, and it looks like my final answer is going to be m plus 3 over 2m plus 1, and that's it for number 11. Number 12. Okay, the top is a difference of squares, so a squared minus b squared will factor as a minus b times a plus b. In the denominator, this is a difference of cubes. There's a special formula for this too. The formula for a cubed minus b cubed is a minus b times a squared plus ab plus b squared. You might want to make a note to yourself if you had forgotten this formula for a difference of cubes. You might want to make a note to yourself to study that. Alright, well, now I can see that I can cancel factors of a minus b. Now, it would be very reasonable if you looked at this and thought, oh, that's a trinomial, maybe I can break that down some more. Okay, I would think it's a very good thing if that was your first instinct when you saw a trinomial, would be to try to factor it some more. However, the trinomials that are produced by the difference of cubes formula are always prime. Okay, so nothing we can do there. I say always prime. If you hadn't already taken out any common factors, they might be a common factor, but beyond that, there's not going to be anything more to do. So my final answer for number 12 is going to be a plus b over a squared plus ab plus b squared. Alright, well, that concludes the set of problems that are of this form where we're simplifying a rational expression. Let's see what's next on our review sheet. Okay, so in problems 13 through 22, perform the indicated operations, give the answer in simplified form. Alright, well, looks like our first one is multiplication. Alright, so in number 13 we have a multiplication problem. Now when you're multiplying rational expressions, it's actually very similar to when you're just simplifying them. I mean, the process is still first factor, then look for things to cancel. So, let me see, starting with this first fraction, x minus 3 I can't really factor, so I'll just treat that as a factor unto itself. Now looking at my denominator, I can see I can factor out a 2, and that will leave me with 2 times x plus 5. Moving to the numerator of my second rational expression means the same thing as fraction. I see I can factor out an x, and that gives me x times x plus 5. And then finally in the denominator I can factor out a 5, and that would leave me with 5 times x minus 3. And now I can look for things to cancel. I see I can cancel an x plus 5 against an x plus 5, and then an x minus 3 against an x minus 3. And then it looks like the only thing left in the numerator will be an x. This numerator became a 1, so I just multiply straight across. 1 times x is x, and then 2 times 5 is 10. It's a 10. You get the idea. So my final answer in number 13 is x over 10. Same idea in number 14. Okay. In this first fraction, there's really nothing to factor because it's already written in factored form. X plus 2 means x plus 2 times x plus 2. If it helps you, you could write it a little more explicitly. X plus 2 times x plus 2. Likewise, x minus 1 cubed means x minus 1 times x minus 1 times x minus 1 times, now in the second fraction we will need to do a little factoring. The numerator is a trinomial, I'll attempt to break that into two binomials. Let me see, it begins with an x squared, so I'll begin each binomial with an x, and then it looks like I'm going to need a plus 5 and a minus 1. Now in the denominator I can just factor out a 2 and have an x plus 2. Well, let me see. So I see I can cancel x plus 2. I can cancel one factor of x minus 1. I'm still going to have two factors of x minus 1 in the denominator. So in the numerator, I'm left with x plus 2 times x plus 5. In the denominator, I still have a factor of 2, and I have two factors of x minus 1, and I'll write that as x minus 1 squared. And that would be my answer for number 14. Alright, on to 15. Maybe take a little sip of coffee here. Alright, now in 15, I see I've got a division problem. So with division problems, this is true for fractions, even very simple fractions that don't have any letters floating around in them. The way that we can interpret a division of fractions is to rewrite it as a multiplication, where we keep the first fraction the same, but then instead of dividing by the second fraction, we multiply by the reciprocal of the second fraction. Of course, the reciprocal is not the same thing, even though that's what I was writing. The reciprocal of a fraction is what you get when you reverse the roles of the numerator and the denominator, when you flip it over, so to speak. Okay. Now that I've rewritten it as a multiplication problem, it's similar to the last two problems. We need to factor it. Okay. Now the x squared minus 3y, I wonder if I miscopied this problem. Let's have a quick look at number 15 on the review sheet. Well, we'll scroll up here. Yes, I did miscopy it. It was supposed to be y squared minus 3y. So let me fix that on my sheet. Yes, this is supposed to be a y squared. I knew something was wrong because nothing was going to cancel. Now, of course, nothing has to cancel, but since the point of these problems is to practice canceling, I kind of expected it to happen. Alright, since it's y squared minus 3y, I see I can factor out a y. So I'll get y times y minus 3. Now the 15, I could think of that as 5 times 3, times 5 over y minus 3. Alright, so I see I can cancel a 5, and I can cancel a y minus 3. And it looks like that's going to leave me with a y over a 3. And that's my final answer for number 15. Alright. Number 16, another division problem. So again, I will begin by recasting that as a multiplication problem. So I'll keep the first fraction the same. And I'll flip over or take the reciprocal of the second fraction. Okay, now what's next? Well, let's bring this all down here to this next line. X minus 3, or x cubed minus 27 is a difference of cubes. So you know what? Let's focus on factoring that on another piece of paper, just as a little side problem. Yes, I think that would be a good idea. Alright, so x cubed minus 27, I could recharacterize that as x cubed minus 3 cubed, since 27 is the cube of 3. Now remember, we had this formula that said a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So I'm going to follow this template to factor this difference of cubes. A and b would be x and 3. So this is x minus 3 times x squared. ab would be 3x. And then b squared would be 3 times, it would be 3 squared, so it would be 9. Alright, so this is the factored form of our x cubed minus 27. So that tells me what to write back in my problem. Alright, so this x cubed minus 27 becomes an x minus 3 times an x squared plus 3x plus 9 over an x plus 3. I'll treat that as a single factor. I'll treat this x minus 3 as a single factor. Okay, and then x squared plus 3x plus 9, again it would be natural to try to factor that since it's a trinomial, but in fact it's prime. And I even know it's prime without thinking about it real hard because I got it over here from my difference of cubes formula, which tells me, yeah, that's probably prime. And I'll tell you what else, even if it wasn't prime, it wouldn't matter because I see I can cancel the whole thing. So there's really no need to break it down into parts. Okay. Now nothing else cancels. I can't cancel these x minus 3's because they're both in the numerator. Okay, to cancel factors, one has to be in the numerator, one has to be in the denominator. All that's left for me to do is multiply straight across. X minus 3 times x minus 3 could be written as x minus 3 quantity squared over x plus 3. And then that's it for number 16. So, moving on, let's have a look at number 17. Okay, so another division problem. So again, I think I'll begin by recasting this as a multiplication problem. Okay, so I want to flip over the second fraction, the one I'm dividing by. So I'm just recopying the first fraction, but now I'll take the reciprocal here. Alright, let's see if we can factor. First fraction, let me see. Oh, I factored that one a moment ago, one similar to that. That's just x plus 5 times x minus 1. Now the denominator I might have to think a little bit about, although I think I did that one recently too. Because it starts with a 2x squared, I'll need a 2x and an x. And now this time I'm going to put the minus 1 in the middle and the plus 1 on the outside, so that when I do the outers and inners I get plus 2x and minus 1. Plus 2 minus 1 adds up to plus 1. Alright, now that 2x minus 1 right there, I'll just treat that as a single factor. Okay, and the x squared plus 6x plus 5, that'll factor as x plus 5 times x plus 1. Alright, so I see I can cancel an x plus 5 and a 2x minus 1, and my final answer will be, numerator will just be x minus 1. In the denominator I have two factors of x plus 1, so I'll write x plus 1 squared. And that's that for number 17. On to 18. Alright, now this is different. This is addition. We've been doing multiplication and division problems, but with addition we need a common denominator. Now you can probably look at 6 and 8 and just kind of think through your head and after a couple seconds come up with 24 as a common denominator. That's perfectly fine, but I think I'm going to take this opportunity to model something for you. Okay, A good way to approach problems where you need a common denominator is to factor both denominators. 6 could be factored as 2 times 3, and then 8 can be factored as 2 times 2 times 2, or 2 cubed. Now, if I look at both denominators, I can see that my lowest common denominator would need to have a 2 and a 3, but it would also have to have a total of 3 2's. So let's make that 2 cubed times 3. And of course 2 cubed times 3 is 8 times 3, which is 24. But now I can compare to that LCD and use it to figure out what's missing in each denominator. In the first denominator, I've got a 3, I've got a 2, but I need 2 more factors of 2. So I'll multiply this fraction, top and bottom, by 2 squared, which is 4. In the other fraction, I've got all the 2's, but I'm missing the 3, so I'll multiply top and bottom by 3. So that turns my fractions into, well, if I take that 4 across, that would give me 4x minus 4 over 4 times 2 times 3, which is 24. And I want to distribute this 3. We're using the distributive rule. So 3x plus 6 over, again, 24. Now the denominators match. Now I can add the numerators, and that just means combining like terms. 4x plus 3x makes 7x. Negative 4 plus 6 makes 2, all over 24. And that's my final answer for number 18. Bada boom. Alright, number 19. Alright, so here I'm combining 3 fractions together. I'm subtracting the first 2 and then adding a third one. Okay. Basic idea is the same though. I need a lowest common denominator. In this case, because all 3 denominators are different and none of them can be factored, my lowest common denominator is just going to be the product of the 3 denominators. X plus 1 times x plus 2. You know what? I think I'm going to have to write it down here. Yeah, I don't have enough room up there. Yeah, the lowest common denominator is x plus 1 times x plus 2 times x minus 1. Which means in the first fraction, I'm missing the x plus 2 and the x minus 1. So I'll have to multiply top and bottom by x plus 2 times x minus 1. Alright, so first fraction, multiply top and bottom by x plus 2 times x minus 1. Second fraction. In the second fraction, I've got the x plus 2, but I'm missing the x plus 1 and the x minus 1. So I have to multiply the top and bottom by x plus 1 times x minus 1. Third fraction. I think I can get this in here. Third fraction, I've got the x minus 1, but I'm missing these other 2 factors, so that's what I need to multiply the numerator by. So x plus 1 times x plus 2, top and bottom. Now when you're adding fractions, you want to multiply out the numerators so that later you can add like terms, but you want to leave the denominator factored. Alright, so in the first fraction, I need to multiply out the x plus 2 times x minus 1. That'll give me x squared minus x plus 2x becomes a plus x and then a minus 2, over my common denominator of x plus 1, x plus 2, x minus 1. Alright, now in my second fraction, let me see here. Let's just first things first here. X plus 1 times x minus 1, that would be x squared minus 1. It's a difference of squares. But then I need to multiply that by 2, so that would be 2x squared minus 2. Now notice that I did not take the subtraction through with the 2. I will eventually need to distribute this subtraction to both terms. And again, we have the same denominator. Alright, and in my last fraction, that should be plus there. Well, let me see. It would be 3 times x is x squared, so we'll have a 3x squared. And then we would have a 2x, and a 1x would be a 3x, but times 3 is 9x. And then finally 1 times 2 is 2, times 3 is 6, over my common denominator. Alright, looks like we'll have to finish this one on another piece of paper. Alright, well, I am ready to combine these fractions. We've got common denominators, so I just need to combine like terms. So x squared minus 2x squared would be minus 1x squared, plus 3x squared would make 2x squared. Okay, x, now there's no x term here, so x plus 9x would be 10x. Okay, now I have to keep in mind this subtraction needs to be distributed to that minus 2. So minus 2, or negative 2, minus negative 2, those actually cancel. Anything minus itself cancels. But then there's also a 6. And then I just have to carry down my common denominator. Okay. Now, I do have to allow for the possibility that it might be possible to factor the numerator and cancel it some more. I do see that there's a common factor of 2. So if I take that out, I get x squared plus 5x plus 3. Okay, now that I've pulled out that 2, it's a little easier to look at this trinomial and say, could I factor that anymore? Well, I would need two numbers that multiply to 3 and add to 5. Okay, I don't think that's going to work out. So this is our final answer. Alright, that was number 19. So I guess now we need to move on to number 20. Alright, another addition problem to do. So again, we're going to need a common denominator. But notice that the denominators could be factored. So we're going to begin by factoring them. That should make it easier to see what our lowest common denominator is. X squared minus y squared is a difference of squares. I can factor that as x minus y times x plus y. Now in the second fraction, one thing I notice here is that I've got a y minus x, which would match up with the x minus y if I factored out a negative 1. Okay, now that I have factored it, I'm going to make a little adjustment. I don't want a factor of negative 1 left in a denominator, so I'm going to go ahead and multiply top and bottom of this second fraction by negative 1. Okay, that'll make the bottom positive, and it'll just put the negative in the top. Alright, so that gives me x. I'm just going to recopy my first fraction. So x over x minus y, x plus y, minus 1, okay, well, let's say plus negative 1. Okay, and the bottom, the negatives will cancel. That was the point. Over x minus y. Okay, now I can see that my lowest common denominator is x minus y times x plus y. That'll cover this one as well. And all I need to do is multiply this second fraction, top and bottom, by second fraction, top and bottom, by x plus y. And then I'll have a matching denominator. Now again, I need to give myself a little more room. Okay, so I'll rewrite this as x over x minus y times x plus y. Okay, plus, I'll distribute this negative x minus y over x minus y, x minus y times x plus y. Alright, now we finally have our denominators matched up. We can add the numerators. And of course x plus x would be 0. Our x plus negative x would be 0. But we are left with a negative y in the numerator. Denominator is still x minus y times x plus y. And that will be our final answer for number 20. Alright. Well, I guess that brings us to number 21. There we go, number 21. Alright, so in number 21 we're doing a subtraction. Subtraction is the same as addition in the respect that we need to have a common denominator. Okay, now I'm going to begin again by factoring my denominators. So when I factor them, the first one is a difference of squares. I can see that becomes x minus 2 times x plus 2 minus, now you know what, I'm going to leave a little space here because I think I'm going to want to bring in another factor to get a common denominator in a minute. So I'll say minus x minus 1 over, now in this denominator I see that I can pull out a common factor of x and get x times x minus 2. So, comparing these two denominators, I can see that if I multiply the first fraction, top and bottom, by x, and the second fraction, what's missing? The x plus 2. So multiply the top and bottom by x plus 2, then I'll have matching denominators. Alright, so for the first fraction, 3x times x is 3x squared. Now I won't multiply out the denominator, but I will put the x in the front, over x times x minus 2, x plus 2, minus, it looks like I need to multiply out x minus 1 times x plus 2, so that's x squared plus x minus 2. Okay, and the denominator is again x times x minus 2 times x plus 2. Alright, now my denominators match. I can subtract the numerators. So 3x squared minus x squared makes 2x squared. Okay, now let me see. I have to be careful here. This subtraction doesn't only apply to the x squared, it also applies to the x and the minus 2. So I want to say minus x and actually plus 2 over my common denominator of x times x minus 2 times x plus 2. Okay, now again, since the numerator is a trinomial, I would want to give a little thought as to whether or not that factors. Okay, but in this case it does not factor, so there's not going to be any further opportunity for cancellation. So this will be our final answer for number 21 right there. Alright, number 22. Very similar to 21. Again, it's subtraction. Again, the denominators don't match. So again, I'm going to begin this problem by factoring the denominators. Alright, x squared plus x minus 6. I'm going to factor that into two binomials. The trinomial starts with x squared. So I'll start my binomials, each with an x. Now I need two numbers that multiply to negative 6 and add to 1. So a 3 and a 2 would work. 1 needs to be negative for the 6 to be negative, but the bigger one needs to be positive since they add to something positive. Okay, so let's make it plus 3 and minus 2. Now again, I'll leave a little space so that I can multiply the top and bottom by something if needed. And again, I want to try to factor this denominator. So let me see. Let's see if we can break this trinomial into two binomials. Trinomial starts with an x squared. So we'll lead off these binomials with x's. And then I need two numbers that multiply to 9 and add to 6. So 3 and 3 come to mind. Now I can look at my two denominators and see that the lowest common denominator would be an x plus 3 times x minus 2, but also there would need to be a second x plus 3 in order to cover the second denominator. So what I'll do is I'll multiply the first fraction by x plus 3 over x plus 3 so that it matches the second fraction in having two factors of x plus 3 in the denominator. In the second fraction, I'll multiply top and bottom by x minus 2 so that it matches the first fraction in having a factor of x minus 2 in the denominator. Now at this point, I'll multiply out the numerators but not denominators. So 3x times x plus 3 would be a 3x squared plus 9x over our common denominator. Okay, and then in that second fraction, 2 times x is 2x. And then minus 4 over x plus 3. You know what, since there's two factors of x plus 3, we could write x plus 3 squared. That wouldn't hurt anything. It'll give me a little room back here. Alright, so for my final answer, okay, I'm going to write my common denominator as x plus 3 squared over x minus 2. That carries over. And then I need to combine like terms. So 3x squared minus nothing is still 3x squared. 9x minus 2x is 7x. And then this subtraction also distributes to that minus 4. That becomes a plus 4. Let's see if we can factor that trinomial there. I think we might be able to do something with that. So 3x squared plus 7x plus 4, if I split that into two binomials, one of them would have to lead off with a 3x and the other one with an x. Now I need two numbers that multiply to be 4, but I also need to get the middle to come out to be 7. So what I'll do is I'll put the 4 here and the 1 here. 4 times 1 makes 4, but then my outers give me a 3 and my inners give me a 4, and that adds to 7. Alright, so it is possible to factor my numerator, but you know what? Neither of those factors matches the denominator, so I won't be able to cancel anything. Since I can't cancel anything, I don't really need to factor that numerator. But I did need to check it to make sure. I needed to see if either of these factors would cancel the denominator. Since they don't, I can leave my answer like this. It would also be okay if you wrote the same fraction with this in the numerator. Okay, you can either have the numerator factored or not. Alright, well, that ends that set of problems, so let's go back and see what's next on the review sheet. We got up through problem 22. Now, in problems 23 through 26, we're going to simplify complex rational expressions. Alright, now when we say complex rational expression, we just mean a fraction that's got fractions within it. So here we have this larger fraction where the numerator is the fraction a over a minus b, and the denominator is a squared over a squared minus b squared. So this counts as a complex rational expression. But it's also just a division of one fraction by another. So we could do this one pretty similar to how we did some other problems. Okay, we could keep the first fraction the same, but take the reciprocal of the second fraction, okay, flip over that bottom fraction, and make it a multiplication problem. And now we proceed the same as we did in other multiplication problems. We need to factor. So, first fraction, there's not really any factoring to do there. Second one, I have a difference of squares that I can factor. So I can cancel a minus b with a minus b. I also have some factors of a floating around. I can cancel one factor of a, and that leaves me with an a plus b in the numerator and an a in the denominator. Now sometimes people are tempted to cross out the a's, but I can't really do that. If I cross out the a's, I would be canceling addition against division, and addition and division are not inverse operations. Okay, I have to make sure I'm always canceling multiplication against division. So that's my final answer for number 23. Now, let's look at number 24. Alright, so again, I've got a larger fraction that has smaller fractions within it. Now in this case, because the numerator and the denominator both have multiple terms, a good approach is to look at all of my individual denominators of the little fractions within the bigger fraction. Okay, and try to identify a lowest common denominator that would cover all of these. Well, it looks like the lowest common denominator that would cover any of these would be x squared. Okay, so what I'm going to do is I'm going to multiply my bigger fraction by x squared over x squared, which means that this x squared will distribute to these two terms, and this x squared will distribute to these two terms, and hopefully, ideally, it'll make it so there's no fractions. Okay, if I'm doing everything correctly, it'll make it so that there's no little fractions within the bigger, there'll still be the bigger fraction. Alright, so x squared times 1 over x squared, well, the x squareds would cancel and I would get just a 1. Now when I do x squared times 1 over x, there'd be some cancellation, but I'd still have an x in the numerator. So I'm left with 1 minus x. In the bottom, x squared times 1 is just x squared. X squared times 1 over x squared is 1. Now notice in the bottom I have a difference of squares. At this point, I've knocked it down from being a complex fraction to being a regular fraction. There's no longer little fractions within the bigger fraction. Sometimes that's all there is to do. But always, if your answer is a fraction, you should look for ways to simplify it. Now here's what I see. I see the denominator is a difference of squares. I could factor that as x minus 1 times x plus 1. And as soon as I see that x minus 1 in the denominator, it makes me think that up here in the numerator, I should factor out a negative 1 to make a factor that matches up with the x minus 1. So my final answer on, this is number 24, is going to be a negative 1 over an x plus 1. Alright, let's move on to 25. So again, it's a complex fraction because I've got this larger fraction, but also within it there are these smaller fractions. Now here, both denominators are x, so my LCD is just x. So I'm going to multiply through top and bottom of the larger fraction by x. So x times x is x squared. X times minus 2 is minus 2x. X times minus 3 over x, the x's cancel, and I get minus 3. Now in the denominator, x times x is x squared. X times minus 5 is minus 5x. And then x times 6 over x would be 6. The x's cancel. Alright, so I've successfully knocked it down from being a complex rational expression, a fraction with fractions inside it, to being a regular rational expression, just one big fraction, no fractions inside it. So again, before I quit, I want to look for opportunities to simplify this fraction. Okay, the top and bottom are both trinomials, so I might be able to break those into binomials. It looks like on the top I could go with x minus 3 and x plus 1. On the bottom it looks like I could go with x minus 3 and x minus 2. So I could cancel out those x minus 3's, and my final answer will be x plus 1 over x minus 2. Alright, well we've got one more of this type, number 26. So again, you can see a larger fraction that's got several smaller fractions within it. Alright, I want to look at all of my smaller denominators, or all of the denominators of those inside fractions. There we go. And identify a lowest common denominator. So it looks like if I just make my LCD xy, basically my LCD needs to be able to cancel all the denominators. xy will do that. So I'm going to multiply top and bottom of my larger fraction by xy. Now when this xy distributes over to this fraction, everything cancels and I'm just left with a 1. But when it distributes to this fraction, the y's cancel and I'm left with an x. Now in the denominator, xy times 1 over xy, well that again gives me a 1. xy times 1 over x, the x's would cancel, but I'd be left with a y. So minus y. Okay, and there's really nothing I can do to simplify that further, so that's my final answer on number 26. Alright, let's go back to our review sheet and see what's next. Alright, it looks like we have a series of problems where we're solving. 27 and 28 are solved for x, so let's go ahead and do those. Okay, 27, I'll just jot this down real quick. We've got x over 2 plus 4 over 3 equals 1 over 2x. Alright, now anytime you're solving a fraction, or an equation that has fractions within it, you want to identify a common denominator. Okay, so again I'm going to look for an LCD. Okay, my LCD needs to have a 2, it needs to have a 3, but it also needs to have an x. So 2 times 3 times x, or 6x. Now here's what I'm going to do with that 6x. I'm going to multiply both sides of the equation by that 6x. So the x plus 2 over 4 plus 4/3, that gets multiplied by the 6x. And the 1 over 2x, that gets multiplied by the 6x. The idea again is we're trying to get all the denominators to cancel. So 6x times x over 2, 6 and 2 cancels and leaves a 3, and there will be 2 x's, so that'll be a 3x squared. Now 6x times 4/3, 6 and 3 would cancel and leave a 2, times a 4, 4 times 2 times x makes 8x. On the other side, x's cancel, 6 and 2 cancel and leave a 3. So I get 3x squared plus 8x equals 3. Now that's a quadratic equation, so I want to solve that by moving all the terms to one side and factoring. So I'll move this term over and make this 3x squared plus 8x minus 3 equals 0. And let's see if we can factor that trinomial into two binomials. Since the trinomial leads off with a 3x squared, one of my binomials needs to have a 3x. Alright, now I need two numbers that multiply to -3. So that's either a -3 and a +1, or a +3 and a -1. Since the middle number is a fairly big positive number, that's kind of a clue that it's probably the 3 that needs to be positive. And in fact, I need to pair the +3 with the +3 that's already there and put the -1 in the middle so that I get 9x minus x makes 8x. Alright, good. Now, since I have two factors set equal to 0, I need to individually set each factor equal to 0. So 3x minus 1 equals 0, or x plus 3 equals 0. So 3x equals 1, which means x equals a third. Okay, or x equals -3. So or x equals -3. Now whenever you're solving a rational equation, i.e. an equation with fractions in it, you do want to ask yourself if any of your potential solutions would make any of the denominators 0, because if they would, you've got to throw them out. Well, the only thing that can make a denominator in the original equation 0 would be 0 itself because of this denominator. Neither of my solutions come out to be 0, so I can keep them both. I'll write them in order, least to greatest, and put them in a discrete set and say that's my answer. There's my solution set. Alright, well that's it for 27. Let's have a look at 28. Okay, same type of problem, maybe just a little more going on in this one. It says solve for x. They give us x over x plus 4 minus 4 over x plus 4. Oh, that's kind of nice. Equals x squared plus 16 over x squared minus 16. Okay. I see right off the bat that these two fractions have the same denominator, so I could just immediately put them together and make that x minus 4 over x plus 4. It wouldn't hurt anything if you didn't do that, but I think it might simplify the problem a little. Now this other denominator is a difference of squares. I can factor that as x minus 4 times x plus 4. And as soon as I do that, I can see that my lowest common denominator is x minus 4 times x plus 4, because that covers both denominators. So, same strategy. I'm going to multiply both sides of this fraction by x minus 4 times x plus 4. Now on the right hand side, that just completely wipes out the denominator, okay, and I'm just left with this x squared plus 16. On the left hand side, I'll get an x plus 4 to cancel, okay, but I still have an x minus 4 times x minus 4. If I multiply out x minus 4 times x minus 4, I get x squared minus 8x plus 16. And I still have an x squared plus 16 over here. Now this is a quadratic equation, so I would want to move everything to one side. But notice when I start moving stuff over, x squared minus x squared cancels, and when I try to move the 16, well, that just cancels. So I'm left with minus 8x equals 0. Well, I can divide both sides by negative 8 and get x equals 0. And it looks like that's my solution. Now, I've got to check that. Does that make any of my denominators 0? Well, it doesn't. It makes this denominator 4, that denominator 4. I'm looking at the original equation. It makes this denominator negative 16. Alright, well, since it doesn't make any of the denominators 0, it's a legit solution. So that's our answer for 28. You could also write it like this. You could write it as a single element in a discrete set. Okay, either way, we're done. Time to look at problem 29. So let's see what's on the sheet there. It says solve for n. Solve for n. And then it gives us 2 over n minus 2 equals 3 over n plus 1. Alright, this problem is similar to the ones we were just doing. Okay, we're again solving an equation that has fractions in it, a so-called rational equation. In this case, the unknown we're searching for is n rather than x, but it doesn't really matter what you call it. We're still going to start by looking at our denominators and identifying a lowest common denominator. In this case, it looks like my lowest common denominator would have to have a factor of n and a factor of n minus 2. So I'm going to multiply both sides of this fraction, both sides of this equation by n times n minus 2. So the left side is 2 over n minus 2. I'll multiply that by n times n minus 2. The right hand side, I've got 3 over n plus 1. So I'll multiply that by n times n minus 2. Now over here on the left side, I see I get those n minus 2's to cancel, and I'm just left with a 2n. Now on the right hand side, I really have to think of this distributing to two different terms. So I really have a 3 over n times n minus 2 plus a 1 times n minus 2. So in that first term there, I get some n's canceling. Still have 2n on the left side, and I'm going to have 3 times n minus 3 times negative 1. And then over here, it looks like I'm going to have an n squared minus 2n. Now at this point, this is now a quadratic equation because of the n squared. That tells me I need to bump everything over to the right hand side. So I'm going to subtract 2n from both sides to get 0 equals I'll put my n squared first. I've got 3n minus 2n minus 2n, that's minus n, and then minus 3. Alright, now I just realized that this isn't going to factor. Okay, now sometimes quadratics don't factor nicely, as in you can't factor them in your head, and there's things we can do when they don't. But at this point in time, I'm expecting the quadratics to factor because we haven't shown you what to do yet in this course if they don't. If they don't factor, as in you could do it in your head. That all tells me that I made a mistake somewhere. And looking back through my work real quick, I see that it's actually right here. I wrote an n minus 1, but that's supposed to be minus 2. Which means that this minus 3 right here should have been a minus 6. Okay. Okay. Well, that's easy to adjust for. That means this should have been a minus 6. Now that'll factor. Okay. So here's what I'm factoring. Here's what I'm solving. 0 equals n squared minus n minus 6. So 0 equals n minus 3 times n plus 2. So I need to set each of those factors equal to 0. And I get n equals 3 or n equals negative 2. So I get two solutions there. Now I do need to check and make sure neither one would cause my original equation to have a 0 in a denominator. Neither one of them does, so I can keep them both. Okay, and that gives me negative 2 comma 3 as my solution set. Alright, well, that's it for number 29. Let's move on to number 30. Alright, so in problem 30 it says solve for A. Now this one is just a little bit different in that there are several letters in this equation. So this is really a formula that is giving us a relationship between whatever the quantities A, B, and C are. Okay. The problem doesn't really give us any context, but this is the type of formula that gets used in circuit theory quite a bit to compare resistances and capacitances. So I mean, it could be something like that, but whatever it is, right now it isn't solved for any of those letters. Okay, but they want us to solve for A, which means to rearrange it so that A is by itself on one side. Okay, as it turns out, our strategy is pretty similar to what we were doing for the previous problems. Okay, it's still an equation that has fractions in it. We're still going to begin by identifying a lowest common denominator and multiplying through by that lowest common denominator so that we don't have fractions, because that simplifies the equation. Now, looking at my denominators, I see I have three different denominators. There's no factors in common. So the lowest common denominator is just the product of those three denominators. So I'm going to multiply both sides of this equation by ABC. So here's the left side of the equation. That will be multiplied by ABC. And here's the right side of the equation. That will be multiplied by ABC. Okay, now on the left side, ABC has to distribute to two different fractions. When I distribute it to 3 over A, the A's cancel, and I get 3BC. But when I distribute it to 1 over B, the B's cancel, and I get AC. Over here on the right-hand side, I would get C's canceling, and I would get 2AB. Now remember, our goal is to solve for A. That means that all the terms that have A's in them need to move to one side. So I'm going to subtract AC from both sides. So I get 3BC equals, On the right side, I just have 2ab minus ac. They're not like terms because the b's and c's don't match. So I can't really combine them, but what I can do is I can factor that a out on the right side so that I would have a times 2b minus c. Now, if I divide by that 2b minus c, I will have solved for a. So this is my answer. The reason this is different than the other problems is I'm not getting a value for a, I'm getting a formula for a, but that was the goal. So like if A, B, and C are all capacitances in an electric circuit, and if I know the capacitances of capacitor B and capacitor C, capacitor, I don't know where I came up with that from, capacitor C, capacitor B, I could plug those in and get the capacitance for capacitor. I said it again, capacitor A. I don't know, I guess I just like saying it that way. Again, you don't need to know anything about circuits. I was just trying to throw in a little context. Alright, well that's problem 30. Let's have a look at problem 31. I think something similar in nature. Okay, it says solve for B. So let me jot this down. Solve for B. And we're given A equals C over 1 plus B. Alright, same idea as the last problem. There's multiple letters floating around in this equation. It's currently solved for A, but we want to rewrite it so that it's solved for little b. Now, there's only one denominator, and that makes it easy to identify our lowest common denominator. It's 1 plus b. So we're going to begin by multiplying both sides by 1 plus b. In essence, in order to solve for b, we've got to get it out of the denominator. And the whole thing will be simpler if we don't have any denominators at all. Okay, now on the left-hand side, I can go ahead and multiply this out and have a plus ba equals c. And at this point, it should be fairly straightforward to see how we would solve for b. We just want to isolate it. So I'll subtract a from both sides of the equation and get ba equals c minus a, and then I'll just divide by a. And that would be my answer. Anytime you're asked to solve for one of the letters in an equation that has multiple letters, your result is going to be a formula rather than a specific value for the letter. But the idea now is that you could plug in values of C and A, and the formula would give you values of B. Alright, well, moving right along then, let's go on to problem 32. I've got to make it so you can see it. There we go. Yep. Alright, looks like we've got one more before we get into the word problems. Solve for L. And what do they give us here? They give us D equals 2 times S over N times A plus L. Alright. Very similar to the last problem. Again, we were given a formula that has several letters in it. It's currently solved for D, which means we could plug in values for S, N, A, and L and get values for D. But we're going to rearrange it so that it's solved for L. Now again, there's only one denominator, so it's pretty easy to identify the lowest common denominator. It's just that one denominator. So that's what we're going to multiply both sides by. N times A plus L over here too. Alright, that completely cancels the denominator on the right side. Distributing the N and the D over here, I get NAD plus NLD equals 2S. Now again, I want to isolate the L, so I'll move NAD to the other side. NLD equals 2S minus NAD. And then I'll just divide both sides by ND to get the L by itself. Cancel, cancel. L equals 2S minus NAD over, all over, ND. Alright, well, blank slate. Next problem. Word problem number 33. Carol can rake her yard in 4 hours. Morgan can do the same job in 3 hours. And Ned does the same job in 5 hours. How long would it take all 3 of them working together to rake 3 of these yards? What portion of the 3 yards would Morgan rake at this? Alright, so 2 questions. Let's focus on the first one. How long would it take all 3 of them together to rake 3 yards? Okay, so I guess that's going to be X. That's our unknown. X equals time for all 3 to rake 3 yards. Alright, the key to problems like this is to think in terms of rates. Okay, rate equals work over time. Okay, so for example, for Morgan, the problem said, well, let's start with Carol. Carol can rake her yard in 4 hours. So Carol's rate would be, well, the amount of work is 1 yard, and she takes 4 hours. So her rate would be 1/4 yards per hour. Okay, now the reason we want to think in terms of rates is because the rates add up. Okay, their times don't really add up, because when they work together, the total time actually gets smaller. But their rates add up. You know, if you and I are working together, then, you know, if you work the same speed I do, then together we're working twice as fast. The rates just add. Now Morgan only needs 3 hours for the same yard. So Morgan's rate would be 1/3 of a yards per hour. Okay, and then what was the other one there? Ned does it in, oh, Ned's kind of the slowpoke. He would need 5 hours to do a yard by himself. So Ned's rate would be 1/5. And again, that's yards per hour. Now, their rate together, now remember, they're doing 3 yards together, so the work would be 3, and the time is our unknown X. Okay, so that'd be 3 over X yards per hour. Okay, now here's the thing. Carol's rate plus Morgan's rate plus Ned's rate has to equal their rate together. So 1/4 plus 1/3 plus 1/5 has to equal 3 over X. Now I just have a rational equation. I can look at the denominators to see that my LCD is going to be, it's just the product of all of them. So 4 times 3 is 12, times 5 is 60. So that's 60x. So I need to multiply both sides of this equation by 60x. Okay, 60x times 1/4 is 15x. 60x times 1/3 is 20x. And then 12x equals 180. So let me see, 15 plus 20 is 35, is 47x equals 180. So x equals 180 over 47. This would be a good problem to get a calculator out for. In a word problem, I think it's pretty much always a good idea. Okay, 180 over 47 would be 3.82. 3.829 blah 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 blah. Now if you just rounded that off and put hours, I would take that, but it's probably better form to convert that to hours and minutes. So what you could do is you could subtract 3 so that you just have that decimal part, and then if you multiply that decimal part by 60, that would give it to you in minutes. So that's about 50 minutes. Okay, so to answer the question, it would take them about 3 hours and 50 minutes. Okay, to do 3 yards. Let's say it like that. To do 3 yards together. Now that other question, let's read that now. Okay, what portion of the 3 yards would Morgan rake if all 3 of them were working together? Well, let's go back to that equation. Remember we said rate equals work over time, but I could rearrange that to say rate times time equals work. See, I know Morgan's rate, and I now know how long they were working. Okay, it was 3.829 hours, or I could just use this fraction, 180 over 47. So if I take Morgan's rate, which was 1/3, times that 180 over 47, that'd give me a 60. That would give me 60 over 47. Okay, or I could say that'd be 1 and 13/47 yards. Okay, so Morgan, of the 3 yards, makes sense. Morgan was the fastest worker, so she did more than 1 of the 3 yards. Okay, Morgan raked 1 and 13/47 yards. Okay. All right. Well, I think that's it for 33. So let's look at number 34. It says Gail drives 10 miles per hour slower than Dexter. With 2 more hours of driving time, Gail travels a total of 330 miles, compared to Dexter, who travels 260 miles. Find the speed and time traveled for each. So that actually makes it seem like there's 4 unknowns in this problem. Gail's speed, Dexter's speed, Gail's time, Dexter's time. Well, let's lay that out then. Gail's speed equals something. Dexter's speed equals something. Gail's time equals something, and then Dexter's time. Well, what did they tell us about the speeds again? Gail drives 10 miles per hour slower than Dexter. Okay, so here's how I'm going to use that. Okay, if I let Dexter's speed be x, then Gail's will be x minus 10. Okay, I'm going to try not to introduce more letters than I have to. Now for the times, again, trying not to introduce more than I have to, I'm going to make use of a relationship between speed, time, and distance. Okay. So let's look at the problem one more time. Okay, with 2 more hours of driving time, Gail travels a total of 330 miles compared to Dexter, who only traveled 260. Okay, so we know their distances. Let's see if we can leverage that. If you can hear the pounding in the background, it's because I have people working on my roof today. But I don't think it'll be too distracting, hopefully. Alright, here's what we're going to use. We're going to use the fact that speed equals distance over time. Okay, but I'm going to rearrange that. That's just the basic definition of speed. You know, like if I say I go 100 miles and it takes 2 hours, 100 divided by 2 is 50, so I'm going 50 miles an hour. But I'm going to bring time up and speed down, just a little bit of algebraic rearrangement to say, hey, time equals distance over speed. And I think that makes sense. And if I tell you I went 100 miles and that I was driving 50 miles an hour, you would know it took me 2 hours. You would know you divide the distance by the speed. Okay. So here's how I'm going to make use of that. Since time equals distance over speed, I know that Gail's distance was given in the problem as 330, so her time should be her distance over her speed, which was x minus 10. Dexter's time, well, he went 260 miles. His speed was x. Now, there's one last little bit of interpreting I have to do. I've got to get this translated into an equation. Let's look at it one more time. It says, with 2 more hours of driving time, Gail drives 330 miles compared to Dexter, who drives 260. So Gail's time is 2 more than Dexter's time. Okay, so here's how we lay that out. First, I need a little more space. Okay, here's Gail's time. 330 over x minus 10. Here's Dexter's time. I know that Gail's time is 2 more hours than Dexter's time, so I have to add 2 to Dexter's time to make it equal to Gail's time. Now I have a rational equation that I can solve. My LCD is just this denominator times this denominator. Okay, so x times x minus 10. So I'm going to multiply everything by x times x minus 10. So 330 over x minus 10 times x minus 10 equals 260 over x plus 2 times x minus 10. Okay, so on the left hand side I've got 330x equals, now on the right hand side again, this whole thing has to go to both terms. When I take the x times x minus 10 and multiply it by the first term, the x's cancel, and I get 260 times x minus 10. When I take it times the second term, I would just get 2x x minus 10. Okay. Well, let's start multiplying stuff out. 330x equals 260x. 260 times 10 would be 2600 plus 2x squared minus 20x. Alright, the x squared tells me this is quadratic. So I want to move everything to this side. So I'm going to subtract 330x from both sides. I want a 0 over here. Alright, we'll put that 2x squared in the front. 260 minus 330 is negative 70. Minus another 20 makes that minus 90x. Minus 2600. Okay, now I see that I have a common factor of 2, so I'll factor a 2 out. That should make it a little simpler. Oops. But now I need two numbers that multiply to give me 1300. And, well, let me see. They have to multiply to be negative 1300. They have to add to be negative 45. Well, let me think. That means the bigger one has to be negative. Okay, they multiply to be negative, so that's one positive and one negative. And the bigger one has to be negative because they add to be negative 45. Here's the first two that come to mind. Negative 100 and 13. Those multiply to be negative 1300, but they don't add to be negative 45. So here's what I'll do. I'm going to grab a factor of 2 out of this and slide it over here. So that'll give me negative 50 and 26. Okay. Well, negative 50 and 26 would still multiply to be negative 1300. But they would add to be negative 24. Okay, now there's a sign that my gap is now too small. Okay, before it was too big, they added to be negative 87, but now it's too small, so I kind of need to go back the other way. What I'll do is I'll start a little differently. Rather than having a 13 by itself, I'll have a 10 by itself. So I'll do negative 130 and 10. Those multiply to be negative 1300. They add to be negative 120. Alright, that's too big of a gap. So I'll shift over a 2. That gives me a negative 65 and a 20. Okay, now those add to be negative 45. So I can say 0 equals 2 times, it'll be x minus 65 and x plus 20. Okay, so that becomes two equations, or one big compound equation. X minus 65 equals 0, or x plus 20 equals 0. So x equals 65, or x equals negative 20. Now remember, x is Dexter's speed. Okay, so it probably doesn't make sense for x to be negative 20. Because it's a word problem, we can use context to narrow down our solution set. At this point, I need to actually read the problem again to see what I'm supposed to be coming up with as an answer. Find the speed and time traveled for each. Oh, okay. Well, I need to fill in all that stuff back at the beginning. Well, I now know that Dexter's speed was 65. Dexter's speed was 65 miles per hour. And his time was, well, let's look back here. Dexter's time was 260 over x. So if I do 260 over 65, that comes out to be 4. And his time was 4 hours. Gale's speed Well, she was going 10 miles per hour slower, so gale speed was 55 miles per hour. And remember, she had 2 more hours of driving time, and her time was 6 hours. Alright, so that's how I'd put my answer for this problem. Gosh, what was it? That was number 34. Let's have a look then at problem 35. I think we're getting pretty close to the end here. 35, 36, 37, 38. Oh, 39. I guess we've got 5 more problems. Alright, to determine the number of trout in a lake, a naturalist catches 138 trout, tags them, and throws them back into the lake. Okay. Later, 58 trout are caught and 22 of them have tags. Estimate the number of trout in the lake. Alright. Well, our unknown is the thing we were trying to find, so we'll let that be x. X equals number of trout in the lake. Okay. Now, if I take the 22 that had tags out of the 58, this gives us a ratio of tagged to total. The assumption that drives this problem is that the ratio of tagged to total in the sample would be about the same as the ratio of tagged to total in the entire lake. So we know there's a total of 138 tagged fish in the entire lake. So 138 divided by x, where x is the total number of trout in the lake, should be approximately equal to 22 over 58. We're going to solve for x, and that'll give us an approximation or an estimation of the total number of trout in the lake. So here, the lowest common denominator, since I have 2 denominators and they're different, is just their product. So we're going to multiply both sides by 58x. So 58's cancel, I get 22x equals, well, let me see, I got to get my calculator out here. 138 times 58, is 8,004. And then I have to divide by 22, and I get x equals, so that comes out to be 363.8 ... So we'll say there are, we'll want to round that up since we're talking about fish. There should be a whole number. There are approximately 364 trout in the lake. Alright, and that'll be our answer for number 35. Alright, 36. Kelly can travel 8 miles upstream in the same time it takes her to go 12 miles downstream. Her boat goes 15 miles per hour in still water. She must have a little motor on the back of her boat. Maybe a big motor. That's pretty quick. I mean, that's, a small gas engine, I would say. Or a really good electric motor. What is the rate of the current? Okay, so that's our unknown. 8 miles upstream, same time to go 12 miles downstream. Her boat goes 15 miles per hour in still water. Got it. So x equals rate of current. Here's how we're going to use that. Okay. When we're going upstream, we're going against the current. So when we're going upstream, the rate of the current, or the speed of the current, is basically subtracted from our normal speed. So it'd be 15 minus x. But then when we're going downstream, speed downstream, okay, my speed downstream, when you're going downstream, the rate of the current is added to your normal speed. So that would be 15 plus x. Now, remember we said before that time, I'll write this off to the side somewhere, time equals distance over speed. I had that backwards there. Distance over speed. Okay, so now if I want to talk about the time upstream, well, it would just be the distance, which was 8, over the speed, which is 15 minus x. And then my time downstream, well, that would be the distance I went over my speed. Well, not me, Kelly, I guess. But here's the key. In this problem, they tell us that it's the same time. So my equation is just this fraction equals this fraction. So if I set those two fractions equal to each other, I get 8 over 15 minus x equals 12 over 15 plus x. The LCD is just the product of the two. So I'm going to multiply both sides by the product of the two. So on both sides of this equation, I'm multiplying by 15 minus x times 15 plus x. On the left side, the 15 minus x's cancel, and I get 8 times 15 plus x. 8 times 15 is 120 plus 8x. Now over here, it's those 15 plus x's that cancel, and I get 12 times 15, which is a bunch. It's 180, minus 12x. Alright, so I'm going to move the x's to one side by, I'll add 12x to both sides. That'll cancel it here. I'll move the constants the other way. So I'll subtract 120 from both sides. And that gives me 20x equals 60. So x equals 3. Okay, so the speed of the current was 3 miles per hour. Alright, well, easy peasy, and maybe not so easy, but we got it. Let's look at number 37, shall we? I think we shall. I shall. I hope somebody's watching this. Alright. 37. Write an equation that expresses a given relationship, then solve for y. Alright, what's it say here? It says x varies directly as the square root of z and inversely as y. X varies directly as the square root of z and inversely as y. Alright, well, when I say x varies directly with something, I mean that x equals a constant times that something. So x varies directly with the square root of z just means that x is a constant times square root of z. So we typically use k as a stand-in for a constant in these kind of problems. And then what else did it say? It also said Okay, x varies directly as the square root of z and inversely as y. Alright, that just tells me that y goes in the denominator here. Okay, normally it would mean x equals a constant divided by y, but when you put all that together it gives you this statement here. X is a constant times the square root of z and divided by y. Alright, that was the first part of the problem, part 1. Part 2 is to solve for y. Well, to solve for y, I would just multiply both sides by y to get y out of the denominator. And so then I would have yx equals k square root z. Then I would divide both sides by x. So y equals k square root z over x. And this would be part 2. And that's it for number 37. Nice quick little problem. Kind of a setup for 38. You know, sort of a warm-up on these direct and inverse variation problems. Alright, let's see what 38 has to say. Alright, the height that a ball bounces varies directly from the height at which it was dropped. Alright, so we've got a bounce height and a drop height. Now let's first interpret that before I read the rest of it. The height that the ball bounces varies directly as the height from which it was dropped. So let's let B equal bounce height. Normally I'd use H for height, but there's two heights here, so I'll use another letter to distinguish them. B equals bounce height, D equals drop height. They tell us that the bounce height varies directly with the drop height. So B equals KD, where K is some constant. But we're probably going to have to figure out what K is. Alright, let's read the rest of it. A tennis ball dropped from 20 inches bounces 12.8 inches. Okay. Well, let's process that sentence. So what that means is when the drop height is 20 inches, the bounce height is 12.8. So you know what? That information is enough that if we plug in those values for B and D, we could solve for K. We're going to need that before we can answer the question at the end. So I'll plug in 12.8 for B, 20 for D. Okay, I'll divide both sides by 20. 12.8 divided by 2 would be 6.4. Divided by another 10 and I'd get 0.64. You can use a calculator too. So I can rewrite this equation as B equals 0.64 D. So in other words, the bounce height will be 64% of the drop height, which sounds right for most balls. I mean, if I hold a basketball out in front of me and drop it, it's probably not going to make it all the way back up to my hands. It makes it about 2/3 of the way. That sounds right. Alright, now we can actually answer the question. The question is, from what height was the tennis ball dropped if it bounces 48 inches? Okay, so they gave me a B value. Okay, they gave me a B value. If I plug that in, I should be able to solve for D. So if B equals 48 inches, then, well, let me plug that in. 48 equals 0.64 D. So I'll divide both sides by 0.64. In order to solve for D, 48 is 3/4 of 64. So that would be 0.75, but I'm I'm dividing by 100, so that actually makes it 75. Okay, and again, you can use a calculator anywhere that you need to. Alright, one last problem on this review sheet. Number 39. Okay. Alright, it says the water temperature in an ocean varies inversely as the water's depth. Okay. So if T equals water temp and D equals depth, then that means that the temperature is a constant divided by the depth. That just means that the greater the depth is, the less the temperature will be. Which again sounds right. Generally, as you go down, it gets colder. Okay. Now hopefully they're giving us some information that will allow us to figure out what K is. So let me see. It says at a depth of 100 meters, the temperature is 7.2 degrees Celsius. Okay, that should be enough information to figure out what K is. So, when D equals 100, T equals 7.2. So let's plug that in. 7.2 equals K over 100. So I need to multiply both sides by 100. Looks like K is 720. So K is 720, and that means that T equals 720 over D. And now I can answer the question. What was the question? Let's see the question. What is the water temperature at a depth of 500 meters? Well, probably less than 7.2 degrees Celsius. Alright, so when D equals 500 meters, M for meters there, T equals 720 over 500. Yeah, that's 72 over 50, or 144 over 100. So that'd be 1.44 degrees Celsius. Alright, well, we are at the end of part 2 of the review sheet. Part 2 I did first this time just because it's the new material. Alright, well, I think that's all I'll put in this recording. But let me encourage you all. Let me flip this back so you can see me. Let me encourage you all that if you have anything else you want me to go over, either with you live on Zoom or that you want me to make a recording for, please let me know. I would be glad to help you. Alright, take care everybody. Bye.